In this week's laboratory, we're going to work on a separation technique, fractional distillation. Right? We're going to separate materials based on a combination of boiling point and vapor pressure, which we know are related because they're both affected by the kinds of intermolecular forces between molecules. If we go back to general chemistry, we can talk about Raoult's law, right? Which, remember, was talking about the vapor pressure of a substance in a mixture, right? The vapor pressure of a substance in a mixture was equal to the vapor pressure of that substance when it was pure times the mole fraction of that substance in the mixture. And if we have multiple volatile components, right, then the vapor pressure of each can be expressed by Raoult's law. And so the total vapor pressure of the mixture is the pressure contribution of one and the pressure contribution of the other, right? And so one of the things we have to remember is, right, any liquid will boil when the vapor pressure of that liquid is equal to the pressure applied on that liquid, which is usually atmospheric pressure. Okay? So for a mixture, when P total equals the atmospheric pressure, the mixture will boil. Okay? Right. So this is a boiling point diagram for a two-component system where each component is volatile, right? And so, right, here we go, right? We have the boiling point of A here, right? So the boiling point of A is lower than the boiling point of B, right? So that means A is more volatile than B. And remember, when we say volatile, right, that has to do with having a vapor pressure. Right? That's what that means to, volatile to a chemist means that it has a vapor pressure. So at any temperature, A has a higher vapor pressure than B. And A has a lower boiling point than B, right? So A will reach the temperature at which it will boil earlier than B will reach the temperature that it will boil, right? And so I disagree with this expression, right? This line is plotting the boiling point of the mixture versus its composition. So this is the boiling point line, right? So what this says here is that, right, if we have 80% B and 20% A, right? That's what this is talking about. So mole percent B. So if it's 80% B, then it's 20% A. If we go straight up, it will boil at that temperature. Okay? And so this line is a plot of the boiling point temperature of the mixture versus the composition of that mixture, right? Now, this line, I agree, is the vapor composition, right? So if we go back here, so let's go with this line since they've got it already drawn here. So we have, right, at 90% B, that mixture will boil at that temperature, right? But the vapor composition at that temperature is this, right? It's only, say, 62% B, right? Which means it's now 38% A, okay? And so that represents, right, if we boil our liquid and then we let the vapor condense, we will get a new liquid with this composition, with more A and less B, right? So every time we boil and condense, right? So if we do a boil, condense, right? The mole fraction of the more volatile component, which in this case was A, increases, right? And that's the basis of distillation, okay? So if we want to separate two mixtures, right? So let's start where they start at 90% B and only 10% A. And say we want to get A. So we boil it, right? It boils at that temperature. Then we let it condense. And now we have a liquid of that composition. Okay? So now we take that liquid and we boil it and we let it condense. And it boils at a lower temperature now, right? Because it's got more of the more volatile component. And when it condenses, we have a liquid of that composition, right? Only 5% B and 75% A, right? Then we let that boil and condense, right? We get that vapor composition and we condense. And now we've got maybe 95% A and only 5% B, right? Let's try it one more time. So we boil it, get a vapor of that composition, and now we've got maybe 99% A and only 1% B, okay? So every time we boil and condense, we increase the proportion of the more volatile component and we reduce the percent of the less volatile component. And that's how we achieve separation. And each one of these boiling and condensing cycles that we're talking about here is called a theoretical plate. Right? And so the question is, how many times do we have to boil and condense our material to get an adequate separation for our needs? So this shows a simple distillation apparatus, right? And so what we have here is a distilling flask, better known as a round bottom flask. Right? And these flasks that we use, right? Remember that your glassware kits are in the cabinets on each side of the work islands in the lab, right? Be careful because some of them, the latches are broken. You know, when you take them out, right? Keep them flat. We don't want to drop a bunch of glassware on the floor. It doesn't bounce well, right? And our kits, right, have ground glass joints, right, that fit together snugly so they won't leak, right? We have a little bit of grease that will help seal those, right? What you do is you just put one thin line of grease on one side of the fitting, and then you insert that fitting into the other side and turn, right? That will smear the grease all the way around, and that's plenty of grease to seal. You don't want a lot of grease to contaminate your mixture, right? So we put things together. There's a distillation head, right? There's an inlet adapter, which is a straight glass piece. Don't forget, right? There's a rubber thermometer adapter. Right? When you put your thermometer in, you want the bulb of the thermometer to be just below the arm of the distillation head, right? Because you want it to be in contact with the hottest vapor just before it crosses over into the condenser, right? So our condenser is a water jacketed tubing, right? There are two. It doesn't matter which one you use. They're the same length, right? You always put water in the bottom and have it come out the top so that it flushes as much air out of the jacket as possible. So the water, right, cools the condenser so that your hot vapor will hit that cool surface. Your vapor condenses into the liquid. A liquid flows down, right? You have a vacuum adapter, right? If we were going to do low pressure distillation, we could hook a vacuum hose on there. We're not going to do that. And then we have a receiving flask. We, instead of using a round bottom receiving flask, we tend to use a graduated cylinder as our receiving flask. Now, the problem with a simple distillation apparatus is it only has one, maybe two theoretical plates. Which often is not enough to achieve a real separation. So it's really only good for things with very different boiling points, right? And we will use it for things like, if we have a material that might be a solid in ether, right? So we sometimes use this to remove solvent from a reaction mixture to recover a solid product. Okay? So this is not what we're going to do this week. The lab procedure says to do both. We're not going to do simple, right? Because the techniques are so similar, right? If we do the fractional distillation, then we will know how to do a simple distillation. Okay? So in fractional distillation, we add a long fractionating column between the round bottom distilling flask and the distilling head, right? And so the extra length, right? So we've got a combination of extra length, and we also do things to increase the surface area. Right? This is showing a packed column, right? So you can pack it with things like glass beads or glass wool, right? We're going to do something different, and I'll show you that later, right? So in this fractionating column, what happens is, right, as we heat our round bottom flask, and we'll talk about how we use a heating mantle, right? So this is our heat source, right? So as we heat this, right, it boils and starts up the column, but it hits the cool material and it starts to run back down. But as it runs back down, it runs into more material that has been heated. And so it heats and it boils again. And then that condenses and begins to run back down. But that runs into material that has been heated and it boils again. And that heats and runs back down. And so this just keeps going on, right? Hot vapors run into the cooling vapors, heat them again, and they boil again and run back down. And so every one of those cycles is a theoretical plate, right? So the more of those cycles we can generate, the better our separation will be, right? And so it just keeps going on, right? It runs into and then runs back down. And that keeps going on until we get all the way to the top of the column. And then once we get to the top of the column, our vapors reach our thermometer bulb. Again, the thermometer bulb lined up just at the lower level of the arm. And then as those vapors come across, they're usually heavier than air, so they sink until they reach the cooled condenser, and then they run in and are collected. And again, we will use a graduated cylinder. Right? Right? And so we got a couple of things here, right? The longer our column is, or the more surface area our column has, we get more theoretical plates. Right? Now, right, our condensers are about 8 inches long. Our fractionating columns are about 8 inches long. Right? I've seen fractionating columns as long as 1 meter. Right? Big, long columns. And this one had, right, a Teflon rod that went down the middle with little Teflon wings on it to increase the surface area. Plus this had a motor so that this spun, so that anytime anything condensed on it, it would be thrown to the walls of the column and run back down more effectively. Right? It was called a spinning band column. Right? And that could separate liquids that had as small a difference as 5 degrees Celsius in their boiling points. Right? It was that efficient. What we're going to use as our fractionating column is something called a Vigoro column. Right? So it's just a straight glass column that someone heated to near melting and then used a glass rod to push dimples into the sides. And those dimples make sharp points reaching into the column, and that increases the surface area. Which increases the number of theoretical plates. And so if we use this Vigoro column and we heat it so that the condensation ring rises gently, right, up the column, we can get somewhere between 5 and 7 theoretical plates out of a column like that. Okay? So this is what our system will look like set up, except remember we will use a graduated cylinder as our receiving flask, right? Just let it drip into a graduated cylinder, right? So you will need a couple of ring stands, and Mr. Wyeth will have made an example for you. So go up to the demonstration table and look at his setup, right? So you clamp your round bottom flask with your sample there. You put your line of grease on your Vigoro column, put it in, turn it 360 degrees to distribute the grease in the joint, right? Then you will put your distilling head on top of that. Again, grease on the head, turn it 360 degrees. That will spread the grease there. You've got your glass thermometer adapter. Do not forget the rubber adapter on top of the straight glass adapter. Position the thermometer so that the bulb of the thermometer is just below the Y of the distilling head. Then you will put on your condenser, right? And all of this is in the hood, right? So we will set this up in the hood, right? Because there is a water source in the hood. Again, grease and clamp, right? With a second ring stand, clamp your condenser in the middle, right, to hold it steady. You put water, you need some rubber tubing to hook to the sink, right? And so water goes in, up through the outside and out, cooling the tube so that the inside of this is cooled. You put on your adapter again, right? Just a teeny bit of grease. Clip the adapter on, and then again we will position this over a graduated cylinder so that we can monitor the volume of our distillate, right? So what comes out is called the distillate. Okay? So what I want you to do, right, what it says is you're going to plot, right, the temperature versus the volume of distillate collected. Okay? So, right, note the temperature when the first drop comes across. So this should go across and gradually increase, right, as the amount of the less volatile component increases a little bit. But then you should get big breaks, right? And so this is really, the transition from mostly one component to mostly the next component, right? And so you can monitor your distillations by looking for those breaks, right? Now, sometimes what will happen is that this will drop a little bit, right? If you notice your temperature dropping and there's still boiling liquid in the flask, that means you're not getting enough heat all the way to the top, right? All the way to the top of your fractionating column to get that next theoretical plate up to the thermometer. So you need to turn your temperature up a little bit, then it will come back up, right? And you can get the next break. So whenever we do a distillation in this class, whenever we do a distillation, we will always collect volume and temperature data in our lab notebooks. And we will do, right, this plot to monitor our distillations, right? Now, you can do this by hand after lab, right, on some graph paper, or you can do it in something like Excel and then, print and cut out and mount in your lab notebook. Okay? But this should be part of your final results after doing any distillation. Now, when we're doing a distillation, we don't use a hot plate or a flame. We use something called a heating mantle. Right? They are designed to fit a round bottom flask. Right? We have smaller ones and larger ones. Right? If you can't find one that fits around your heating mantle, what you can do is put your round bottom flask down in a larger mantle and then surround the round bottom flask with sand, right? The sand heats, and then you still get even heating along the surface of your round bottom flask. Now this round bottom flask is probably overfilled, right? You only want it about half full, right? So you pick your round bottom flask size to give you maximum surface area. And the maximum surface area is when that round bottom flask is about half full. And then that gives you room for bubbles to form without those bubbles splashing out of the round bottom flask up into the condenser. Okay? And a heating mantle is controlled by a rheostat type controller. Right? Now, some older heating mantles actually have plugs that will go directly in the wall, but you do not want to put them directly in the wall. Note, right? There's a plug on the rheostat controller. So the mantle is plugged into the rheostat controller. The rheostat controller is plugged into the wall. Now, most of ours are designed a little bit differently, right? Some of ours, the heating mantle is actually contained in a box-like container. You don't have to put it on a ring stand like you would this kind, right? And so those have, some of them have their own controllers. Some of them have dedicated controllers that you plug them into. But you want to set your controller so that, right, if this is our fractionating column, right, as it condenses, you will get drips coming back. Let me change colors here to make this easier to see, right? You'll get drips falling back into the solution. You want it to be going at about 1 drip, that's a P, per second. Okay? That is a reasonable mild boil. Okay? So we're looking to heat it to a mild boil. Right? Whenever we boil something, we will use boiling chips or boiling stones. Right? And so these are a variety of things. They can be glass beads. We have some that are little Teflon chips. And we have some that are actual stones. They're, I think, calcium carbonate type material. Right? They're all there in the laboratory. But what these do, right, these go in the bottom of your flask, right, with your liquid above it, right? These provide a nucleation site which lets bubbles form smoothly, right? If you boil without these chips, we can get we can get a sudden explosive boiling that we call bumping. which can splash material up into your fractionating column, right? Or if you're boiling something in the open, it can cause an injury, right? Because what happens is these very pure liquids, especially non-polar liquids, can do something called superheating. That is, they can heat above their boiling point temperature without boiling. But then when they do boil, the whole mixture boils at once. And so it explodes. This is what happens, the story of distilled water boiling explosively in a microwave oven is a story of superheating, right? And so we don't want that to happen. And so boiling stones keep that from happening. And so anytime we boil liquids, right? Anytime we boil liquids in the laboratory, we will use boiling chips or stones. Okay, that is a must. The molecules we're going to be separating are ethyl acetate and butyl acetate. If you look at this structure, right, this structure in both of them makes them esters, right? As esters, that ester group is very polar, right? And so these molecules are attracted to each other by dipole-dipole interactions. If we break down the name, we see this part of the molecule is the same in each. Right? That is a derivative of acetic acid minus the hydrogen. And so that is the acetate part. Right? Modifying that is 2 carbons in ethyl acetate. So that's the ethyl part. Modifying that is 1, 2, 3, 4 carbons in a chain. That is the butyl group. Ethyl acetate has a boiling point of 77 degrees. Butyl acetate has a boiling point of 126, right? Meaning we have to increase the temperature, right, to get the butyl acetate to boil. If we look here at 20 degrees Celsius, the ethyl acetate has a vapor pressure of 73 millimeters of mercury, while the butyl acetate only has a vapor pressure of about 8 millimeters of mercury at the same temperature. Right? If we go up to a higher temperature, ethyl acetate has a vapor pressure of about 284 millimeters of mercury at 50 degrees Celsius, while butyl acetate only has a vapor pressure of 63 millimeters of mercury at 50 degrees Celsius. So at all temperatures, ethyl acetate has a higher vapor pressure than butyl acetate. And so we say that ethyl acetate is the more volatile, right? When we say something is volatile, we're talking about its vapor pressure, right? So in organic chemistry, volatile means it has a higher vapor pressure. And so at any moment in the vapor above our liquid mixture, we're going to have more ethyl acetate than butyl acetate, and that's what we're trying to use then to separate them. We're going to start with a mixture of ethyl acetate and butyl acetate, and in this mixture we don't know the ratio of the two. And so what we're going to do then is we are going to plot the temperature that we read at the top of our distilling head versus the volume of distillate collected. Right? And for a fractional distillation, you get no real temperature change, and then it'll jump up, and then it should plateau. And that plateau is approximately the boiling temperature of the lower boiling component. In this case, the ethyl acetate. That is an abbreviation for ethyl acetate. Then, as the ethyl acetate boils off, the temperature should start to rise until it reaches something close to the boiling point temperature of the butyl acetate. Right? And so what we want to do then is take this collected volume, right, where it's clear, and use that as an estimate, right? We want to estimate the fraction of ethyl acetate in our original mixture. Okay? Now, a couple of things to remember. Boiling is a physical change. We're not changing the identity of either molecule. Right? We're only boiling them and then recondensing them, and hopefully recondensing them in a way that separates the more volatile component, the ethyl acetate, from the less volatile component, the butyl acetate. And so we have to remember, in a physical change, there's no chemical reaction, so we don't have to worry about that in our pre-lab. Right? And there's no, therefore there's no mechanism. So you don't have to worry about that as part of the pre-lab. Okay? So make sure you read the complete laboratory procedure. Know how to put together either the simple or the fractional distillation. So you'll need to write out both of those as new equipment. There will be one set up in the laboratory that you can use as a model to help you set up when you get there, but you'll need to have both of them listed in the new equipment. Also, since there's no chemical reaction and no mechanism, there will be no theoretical yield. Okay? We'll see you in lab.